Hi, everybody, and welcome back to the continuation of Chapter 2. Now we're going to discuss some of the statistical pieces of psychology. Mind you, I know you have to take statistics as its own course. So this is just, again, an introduction to some of the terms and really what it's important to think about and think critically about psychology specifically. We'll begin with the population. The textbook is going to tell you that it's a complete collection of people, which is rarely measured. Now, the reality is a population is the complete set of something we're trying to study. A population is probably best thought of as, say, all Canadians. But if I was interested in how do students perform in intro psychology, my population might be all Canadian students taking intro psychology only. From that population of students, I might get a sample, which is I might pick a few here and there across all of the institutions in Canada and ask them questions about their experience in intro psychology. So a sample is a subset of the population, or as the textbook says, a partial collection of people drawn from the population. So the population is sort of the everybody involved in something, whereas the sample is a subset of that. So a few people from which. I remember, and I teach statistics, that when I tell my students this in that class, I'll tell them that, you might think, how many people do I need to get a really good idea of what people's opinions or thoughts or behaviors are on some topic? And George Gallup had a really good analogy for this. It was, imagine you have a bite of food. It's a bowl of soup, for argument's sake. If you take the first, sip of that soup and it's too salty, do you need to eat the rest of the bowl of soup to know that it's too salty? And the obvious answer is no, of course not. A sample is like that first spoonful. As long as it's collected in such a manner that the representation of the things involved that we're trying to learn more about um, represents the population somewhat randomly, equally, then it's like that spoonful of soup. We don't need to get any more. We know it's too salty. So in psychology, we realize that we can't always ask everybody of a particular group a set of questions. And the reality is, we don't need to. Samples suffice. I'll tell you more as to why if I get to teach you statistics, but that's probably good on this particular slide for right now. Ultimately, when we collect data, one of the things we want to do is graph it. In statistics, we call this exploratory data analysis. And here, really, we're just saying it's a graphic representation so we can see what's going on. And then we use what's called descriptive statistics to describe the data. Think of this as the average grades you have in university or what you came out of high school with. You may also think of it like variability of grades. So that you may have a particular grade, but maybe I'll ask, how well did other people in your class do? We know that we all didn't do the same, didn't have the same performance. So descriptive statistics really describe the data set in terms of, on average, how well people did, which is measures of central tendency, as well as the variability or how the data varies. Graphic representations can help to describe things like the frequency of which responses occur. And imagine if we really plot a graph based on the frequency of how things occur. So let's say I asked you, what is the meaning of life? What I might try to do is find answers that are similar and I'll code them so that the frequency at which they occur, I'll denote it with like a tick. And the number of ticks I get for the same answers will help me get a better indication of if people think similarly on something like the meaning of life. Now, ultimately, we also deal with things that are called a normal distribution. And this technically says it's a mathematically defined frequency distribution in which most measurements are concentrated around the middle. That is probably really meaningless to you or hard to visualize. A bell-shaped curve is another way to think of a normal distribution, but I recognize that also might be a bit confusing or ambiguous. So if you'll humor me, go find some dice. Just get two die, and then you're going to create a frequency distribution. So you're going to roll them, and you're going to record the frequency or the number of times each value appears. You know you can only get as low as two, that would be two ones, or as high as six, or 12 rather, two sixes. So if you do this and you roll the dice, what you're going to see is that if you think about it even now, how likely are you to get 2 or 12? And the answer is not likely. And we know that they can happen, but they're probably not going to happen the most frequently. So when you create your frequency distribution, you're going to notice that really you're going to have more of the 6, 7, 8, 9 values occur. And if you sit there and actually take the time to do this, you'll notice that with frequency on the x-axis and then the number that occurs on the y, eventually, if you roll enough dice, you'll see that a normal distribution will occur. Now, that's a pretty nerdy way to do it, but it does work. If you take the time to do it, you'll see it. It'll happen. But what does a normal distribution mean? What does it really tell us? It can give us some predictive way to anticipate the likelihood that certain behaviors may or may not occur. You can think of it as telling us really normal as a behavior has a broad set of values of what constitutes normal, and abnormal has far fewer behaviors. And you all know people that you would think that are normal or abnormal as whatever those things mean to you. But let's think about happiness distributions. Maybe if we think about the bottom, and we'll start down here, the purple line represents a normal bell-shaped curve where most people would probably have a level of happiness that's around about 5.5, it says. But if we actually ask people, maybe men and women, how happy are you? We can take this data and plot it to figure out, are there similarities or differences in how men or women experience happiness? And we can compare this to a normal distribution, but I don't want to side tangent too deep into statistics because I know that this is not that course. So graphing the data allows us to really see what we find when we ask people questions like, how happy are you? And we can also plot it against what we expect to see, which is that normal distribution of values. In this instance, we can see that there are far more females that were surveyed or sampled about their happiness than there were males. Just the numbers say so. But the levels of happiness, where do they peak? They both seem to peak around 8. So even though there are more females contributing answers about happiness, both men and women seem to be equally happy, sort of. Descriptive statistics really describe the center of a normal distribution or the center of a curve. And these are usually indicated as the mean, which is your average. It can also be represented by a median, which is the middle number in a rank-ordered distribution, or the mode, which is the most frequently occurring number in the data set. If we have numbers 1, 2, 3, 4, 5, the median is 3. The numbers are rank ordered and it's in the middle. If we went 1, 2, 3, 4, 5, 6, now we would have 3 and 4 in the middle. So we just add them up and divide by 2 and we get 3.5. If we have numbers 1, 1, 2, 3, 4, 5, the mode is 1 because it occurred twice. It's really that simple. The number we typically use, or the measure of central tendency, rather, we use in statistics is the median, but the median has value. It's not influenced by outliers or influential observations, but we'll leave that one there for now. Skewed distributions just mean that the shape of things, like we can see in an example here, back to happiness, is that the data, when you look at the bottom, the normal curve, what we would expect is the purple line, and we see that In both cases is a negative distribution, like a negative skew. That just means that the tail points to the left. Positive skew would be the opposite. The tail would fall to the right. Excuse me. So because this is a skewed distribution, we could make note of really what that means, but let's leave it for now. The the skew just refers to tails to the right or tails to the left. And to the right, it's positive. To the left, it's negative. Now, the slide's right here. So you can see positive skew, tail falls to the right. Typically, we deal with normal distributions. And in the other case, you can see the negatives, the tail goes to the left. So let's think of as an example here to help illustrate it. We look at a population based on age. In the left, we would say that we have a population where there's a lot of young people and few old people. On the far right, the negative distribution, there are few young people and lots of older people. And in this here normal distribution of age, we'd probably have people as an average age of something, and then we have an equal number to the left that are younger, and an equal number then to the right, because it's symmetrical, that are older. Now, the center of the distribution is typically, I said, the mean. It could also be the median or the mode. But it's also interesting to think about how variable our answers are. Now, I started with a really complicated question I posed just a moment ago about what is the meaning of life? You can appreciate the variability of responses we might collect if we actually asked people that question. On the other hand, if we think about how many ears we all have, we're probably going to conclude it's two. And there's very little variability, meaning most people that we come across have two ears. And I recognize someone may not, but it's exceedingly rare to see. So there's very little variability in that particular assessment. When we talk about the range of values in statistics, we refer to the min and the max value. It doesn't give us a lot of information about a data set, but it does contribute something. And then the standard deviation. So let's go back up to variability, how variable a response is. There's a measure we can calculate called variance that is a measure of variability, of how these data points differ. The standard deviation, by definition, is just the square root of the variance. So it's effectively a measure of variability that we use because the square rooting of numbers, which, and I recognize this means nothing to you, it just brings it back into the units or values of the units represented in the beginning. So it's just according to the book, a statistic that describes the average difference between the measures in frequency distribution and the mean of that distribution. But that's a bit confusing. By definition, it's literally just the square root of the variance. And the reason we measure variability is because we know we're not equal. We know that we're different. And those differences are important to measure. It's important to know how average we are and think of your own grades. What's your average grade? And then what is the measure of variability? Meaning, do you do better than average in some courses? Of course you do. And do you do worse than others? Sure. If that spread or measure of variability is rather narrow, it gives us some information about you. So if we came back to just looking at a graph as an example, let's take the normal distribution in the middle. In this instance, imagine we could squeeze those lines closer together towards where the mean is in the middle. If I gave you a test and the shape of that distribution became narrow, so it's basically coming together and peaking towards the middle, that tells me there's little variability in the data, which is a way to say you all have the same amount of knowledge of psychology. So a distribution that's very narrow has little variability. If it's about your knowledge, you all have the same amount of knowledge. Now imagine we could pull these lines apart and make it flatter in shape. And we still gave you a test, but the test gave me data that's creating a distribution that's flatter or more spread out or more variability. That's a scenario where you all really have different levels of knowledge of psychology. It's a little bit terrifying, to be honest. as it would be if you were all had the same amount of knowledge. The reality is neither of those instances really happen. And what we usually get is more like a normal distribution where people perform fairly well. Some do better, some do worse. So that's, when we think about statistics and values, how we can really think about what the data set tells us when we look at similarities and differences. So here, when the curve becomes much more narrow and higher, it might allude to the fact that there's little or less variability in something we're looking at, maybe like your grades. If it gets a little bit more spread out, it could still look like your knowledge in the course, just your grades on the test would be very different from each other. Of course, there's also times where we collect data from things and we get distributions that they overlap. So you can see where the purple line and this brown line um, share some common ground, if you will, but the averages, if we look, they're not exactly the same. They're a little bit different. This is more in line, and I'd probably pull them further apart. If we think about something like drinking and driving a simulator versus being sober and driving a simulator, we might see that the graphs, when plotted, they may have some overlap, but typically the average response time of people that are sober is significantly faster than those that have been drinking. So because the reaction time would be longer to, say, apply the brake and you're driving a simulated vehicle, that's saying that alcohol is influencing your reaction time and that you don't act like you would if you were sober, where you would be faster. So when we think of these graphs, that's where we can start to really compare things to see how similar they are, which means how much they overlap, or how dissimilar they are, how they pull apart. I think we should start the discussion on correlation with a really important statement. Correlation is not causation. The reality is, when we look at correlations, we're trying to determine how variables are really related to each other. So, what's the relationship between them? In this instance, the example saying, how many hours of sleep do you get? And then let's, instead of thinking how many presidents you could name, we could make this your test performance out of 50. So forget number of presidents, recall the sleep, and think about it as your test score. So if you don't sleep, your test scores are pretty poor. And if you keep looking at the hours of sleep, if they increase down, FGH all the way to L, as sleep increases, the grades increase in value. Now, do you think that would really be the case? That the more sleep you get, the better you would do on a test? Let's think about that for a second. It's saying you just need to get more sleep to do better on a test. What isn't it measuring? It's not assessing, did you come to class? How many hours did you study? And so on and so forth. That's the challenge about correlation and why it isn't causation, is that, sure, we might agree that sleep is important for your performance of a cognitive test, or if you're naming presidents or hypothetical writing a test, but it's not the only thing that's important. There are probably other variables we can consider that might explain why you would do well on a test. In terms of continuing with correlation, we can look for synchronized patterns of variation. We can measure how these pairs of variables are related or not to each other. We can repeat this over and over, make a series of measurements, and try to figure out really what's going on. When two variables are correlated, we can gain knowledge of how one can be used to predict the value of another. Now, a great example of correlation that comes to mind right now was the announcement made that Tylenol is somehow linked to autism. Now, before that, it used to be vaccines and autism, specifically the measles, mumps, and rubella vaccine, or the MMR vaccine. And the reality is, there is insufficient evidence to suggest that there is a correlation or any relationship whatsoever between Tylenol nor a vaccine causing autism. I understand that some behaviors are complicated, and some discussions, you may not be sure of why things happen, and you may Google and find something on the internet that says this, is the case because of whatever reason. But the reality is there is no data to suggest that that's the case. Like, period. There's none. So correlation itself is about looking for relationships that are either positive or negative. Now, positive is just simply the more sleep you get, the better the grade you would expect to receive. Negative is not the opposite. Like, the less sleep you get, the better you would do. In fact, that would be a positive correlation. So positive is just that the variables move together. Less sleep and better grades. So the more sleep you get, the worse your performance would get. It just moves in a way that would be consistent. The negative is a less scenario. So think of happiness. The more sleep you get, the less happy you would find. It's just the inverse relationship. So it's basically positive is that you increase or decrease, it moves the same direction. Negative is the opposite, so that less is more or more is less. The more money you have, how happy are you? What do you think that relationship would be? Would it be positive? More money you have, the happier you become, or would it become negative? Would it be both? Is there a limit to the degree of how happy we would be and how much money we make? Maybe. Of course there is. But just because you have money doesn't mean you're happy? No, not necessarily. Correlations range from values between -1 and +1. The important thing about the values is just it's the absolute strength that's most important. -0.87 is a stronger correlation than +0.7. That's it. If it's zero, it means there's no correlation. The correlation coefficient is denoted with the letter lowercase r. So when we graph correlations, you can expect with causal relationships, and I should probably tell you that in causal conclusions, there are, of course, correlations, but correlations don't imply, I said, causation. So the graph of a perfect correlation of +1 or -1 would look like the top and then middle graphs, respectively. The bottom figure shows a zero um, correlation score or coefficient, which is really saying there is no relationship amongst the data. It's rare when we think of studying variables and performing correlations, to see these perfect scores form, but you can see they basically form a line of best fit, or that the points would fall on the line. It doesn't show you other values, which really are helpful to see, but again, this isn't statistics. We'll just have to unfortunately wait till you get there, or fortunately wait till you get there, to go into this into more detail. Oh, I lied. Never mind. The next slide had it. Um, Correlation of zero point 0.5. It's a really good one. Comparing it to zero a second ago, is that something you need to think about is what value of a correlation provides us with a great prediction of a relationship. So if a correlation of 0.1, the range, remember, is -1 to +1. But as we can see, 0.1, look at all the data points around that line. They're really not on it. Most of them are far away. And that's not that surprising, because a correlation of 0.1 is terrible. It's really, really low. Or to just say really weak. Similarly to 0.3, the line you can see that's graphed here, most of the points are not on the line. That's, again, it's at best a moderate correlation, similar to 0.5. That's really more like a moderate but not strong correlation between variables. But the slide's really useful in showing that as we go vertical of the figures, the lines get closer, the points get closer and closer to the line, which is why you can imagine if that line of best fit was imposed here, it'd be directly on it. And in the case of zero, it'd be nothing would be on it at all. Now, causal relationships really are the hallmark of something causes something to occur. Like if you drink or consume alcohol, at least enough of it, you will become intoxicated. So in the real world, we know that if you drink alcohol, we see a change in your behavior, meaning we can see that there's a relationship. If we studied it from a correlation perspective, yeah, of course they're correlated. But the challenge with causation with variables as it pertains to a correlation is that how do we know there's not some other third variable to account for what's going on? Remember, if we come back to sleep and academic performance, you might think the more sleep you get, the better you will do. But that's probably contingent on studying, which in this case would be the third variable. If we don't assess, which in this case, correlations typically don't assess all of the other variables that predict a relationship to some behavior, then we don't know why. We're left speculating. Could it be studying? Sure. Sounds reasonable. Could it have been an easy test? Sure. Possible. Basically, I can't rule anything out because I just don't know. So think of something like um, we see and hear this a lot about violence and video games. And, in this case, it says exposure to media like violence. And does it influence aggressive behavior? So it might be the case if you watch violence or play video games, that maybe you'll be more aggressive. But isn't it also possible that maybe you're just naturally more aggressive and you like to play video games? Or maybe you're naturally aggressive and you like to watch the news or watch violent media? I don't know. What's the other unknown variable? Maybe it's if your parents aren't there, you'll behave a little bit differently than if they are. Um, I have no idea. There's going to be a million other reasons as to why we do and think about the things that we do. It's not always just saying that video games cause people to become more aggressive. No, there's no data to support that. But is it possible you could play a video game and get frustrated and become aggressive briefly? Sure, absolutely. But if you watch the news, which has populated with, well, very difficult things, including death and murder and war, does that cause people to go out and become aggressive? So why would video games somehow be different than watching news or various media outlets? It- it's not. And that's the reason that all of these examples get complicated is there's no clear crystal path or a crystal ball to say this is the thing that it is. We just ultimately don't know. Experimentation, on the other hand, is how we can try to establish what the causal link is between some variables and a predictable behavior. So we're trying to ultimately eliminate differences between these groups when we examine them. So imagine we remember sample from the population. So let's just say we're considering the relationship between violence and behavior. We might go out and get a group of kids. So we're going to sample from the population. We're going to give one group exposure to violence, whatever that is. Let's think of this as a Bobo the Clown study was actually performed. A group of kids watched an adult go into a room with a bunch of toys and interact with the toys. In one instance, the kids watched the adult punch this Bobo the Clown punching doll toy. It's one of those, you may not remember this, but there's toys with like a weight built into the bottom. Think of like a big balloon with a weight. If you punch it, it goes down like a punching bag and comes back up. So basically, the adult punched and kicked the clown, and then the kids were allowed to go in and play with the clown and the other toys that were in the room. This group watched an adult go in where that clown toy was, but the adult never interacted with it. The adult interacted with the other toys in the room. The kids were then sent to go in and play. And we can think about, were they exposed to violence? Yeah, all four were. And what did we observe? They all had high aggression. And in fact, when children watch an adult beat up the clown doll, you can guess what they did. They went in and beat up the doll. And the other group that went in, where they weren't exposed to violence, guess how many kids interacted with the doll in a violent manner? You've got it. None. They didn't. because they didn't see or weren't exposed to how to play with it, in an aggressive manner. That's why we do research in a controlled environment like a laboratory. We can make sure all of the experiences are the same. We can control for other extraneous variables. And the only difference between the two was the observation of violence. Now we can see what happens. So, this is where things like independent variables are important because as a researcher, we control the independent variable by manipulating it, creating at least two different conditions. In this case, one that viewed violence and one that did not. If we think about drinking and driving as an example, I could have a group of people drink beer and then become intoxicated and drive a car, or I could have another group drink non-alcoholic beer and let them think they are and drive a car. I don't have to tell you what I think or what you're getting to assess how you would respond. But what we measure is the dependent variable. I can control what you're drinking, as an example. We can control what you're exposed to. We can't control how you act. That's why we record your behavior. This is true of human research as well as non-human or animal research as well, just to throw it out there. Ultimately, when we're done, we compare each condition to see if the data is similar or different. This will be using descriptive statistics like averages, looking at the variability of responses, and then graphing to see how does things look. The important thing to consider when we do experimental research is random selection, where we randomly select people from the population to participate, and then we randomly assign them to a condition where they would see violence or not. We don't just look at someone and say, okay, you're going to get this. No, you're going to get that. No, we determine these conditions before participants ever show up. So that's as random as possible. We don't allow them to self-select because imagine that we tell you, hey, you're about to participate in a study. You can either get drunk or you can be sober. Think about how that would influence the potential results. What would you decide to do? And you might think, oh, I would love to be in the drinking condition. Maybe, but would you love to be hungover by 5 o'clock in the afternoon? Not necessarily. And maybe you don't drink, and maybe you might feel pressured to, et cetera, et cetera. So that's why we never allow the selection of people to be in a particular group or not. Hopefully, this makes sense. When we conduct research, we randomly select people from a population. They're our sample. We then randomly assign them to a condition, violence or non-violent, and then we record to see what happens. Maybe we can throw in another variable like adult supervision. What if an adult is in the room? Will it change how they act when they're exposed to violence? And the answer seems to be, hypothetically, no, that nonviolent exposure, regardless of adults there, didn't change their behavior. But up top, look at this. Even with an adult present, it didn't matter. They still acted out. They were still acting more aggressive. These are, of course, hypothetical examples, but it's important to think about all of the variables that experimenters are able to control, to manipulate, to try to assess what really drives various behaviors that we can observe. Sometimes it's kind of weird to jump back to these things because there's some fun graphs that I use in statistics, like I think it's number of drownings and amount of cheese consumed in the US. Sometimes things will call they'll autocorrelate. Let's just forget that for now. But sometimes when we think about science and maybe refugee incidents over a period of time, how do people basically respond with anti-refugee posts corresponding to anti, if you will, refugee incidents? And sometimes it's not random. Sometimes they're related. So when things occur, um, especially in incidents, that people respond accordingly. Um, I'd rather not dig into examples like this, but I think this one's pretty self-explanatory that it's not surprising to see when incidents occur that people are more likely than to respond how they don't like, um, you know, refugees, for argument's sake. It's a contentious example because of what's going on politically right now. So I'd rather maybe leave this one just because it's complicated. Statistics is important because the method is used to calculate or to gather the data and the rules in place of what to do with the data, like getting an average. But statistics is really the procedures for taking these numbers and making them meaningful. And generally, we have a significance level in psychology that is zero point 0.5 or 5%. And what that means is generally, we're not accepting the results of a study unless it says there's less than a 5% chance that those results would have occurred randomly. So let's think about this a little bit differently. You think of pass fail as 50% and above, like you pass or below you fail. Scientifically, in order for a study to pass, it really has to be over 95%. Anything below 95 is a fail because we want to have a strong degree of certainty. The results we have aren't just due to dumb luck. They're not just due to random chance. So that's the kind of value we've established that allows us to draw conclusions or not, depending on what the data say between groups. So it's really this value we calculate, like the probability, the odds that something has happened, not due to chance, but due to the manipulation of variables that we control and the behavior recorded. If something is statistically significant, let's say alcohol consumption and reaction time, that means the group of people that are sober are significantly faster. They're quicker to respond than the group that is intoxicated, meaning they're significantly slower. If the results are indicated by a p greater than 0.05, this is to say there's greater than a 5% chance of the results being explained due to chance alone, which is not good enough in science to say something works or something's significant. So in that case, we would say there is no effect. So if we think about trying to think of situations where what works. I remember a friend of mine studied ginkgo biloba, trying to figure out, does it improve memory? And every study of the 10 studies she did were not statistically significant, which means it didn't seem that taking the herbal supplement resulted in any increased memory performance. Now, the claims are that it helps boost your memory, and she failed to find evidence to reject the null, meaning the rats performed exactly the same, regardless of the treatment they received. So that's suggesting it doesn't work, as an example. Now, the real world, there's a lot of likelihoods or different scenarios where we could find things that occur due to just coincidence. Now, imagine we ask, students, do you believe in extrasensory perception? What do you think? So, if we don't, by not using probability theory, people will routinely underestimate the likelihood of coincidences. Let's give you a real coincidence. Now, I just mentioned vaccines not being related to the outcome of diagnosing autism as an example. The reality is the MMR vaccine is given to children at around 18 months of age. And sometimes for some children, the onset of symptoms of autism occurs at 18 months of age, meaning there's a coincidence about the timing of the vaccine and the onset of genetic, we'll just call them switches, where the genes are expressed, where the child now develops a little bit differently than before that time. So the reality is that the most astonishingly incredible coincidence imaginable would be the complete absence of all coincidence. Of course, it's likely that we might notice two things occurring simultaneously and think they're somehow related. I get it. I could see why a mother might be like, wow, I went to the doctor and nothing else changed, and it must be the vaccine that caused autism, when the reality is it doesn't. It just happens to be a coincidence. When we like to draw conclusions, we want to think about studies, their purpose. What's the validity of the things that we do? Now, in my class, and it's important still for you as an online class, that when I've talked to my colleagues that really study and are knowledgeable of validity, it's really more important just to think about validity itself. There are several kinds, but let's just say, what is validity? What does it mean to be valid? I also don't know if these images are really reflective of the point they're trying to make with validity, but imagine that I have to give you a test. And let's just say I gave you the wrong test as an example. I think it's pretty obvious that that's not a valid assessment of your knowledge. But if I gave you the wrong test, like human neuropsychology, and you didn't perform very well at all, and then I said, oh, I'm sorry, I'll give you a makeup test. And then I made a mistake and gave you another test that was also incorrect, let's say statistics. You may perform consistently poor on both assessments because they're not valid, but they are reliable. They are reliably confirming that you don't know the material of those other classes. But that's not a measure of validity. So things can be reliable, like you consistently do the wrong thing, but it doesn't make it valid. If it's valid, though, it does make it reliable. So if I actually give you a test of intro psych and you perform how you all do, I could, in theory, make another random test and give it to you, and you should probably perform exactly the same, or at least very similar to the previous score obtained. Thus, you have validity or a valid assessment of your knowledge, as well as reliability in the knowledge obtained from the course thus far. Hopefully that makes sense. Rather than think about these terms as really different things, because some of the context of what validity is like face validity. It would make it really confusing compared to what I just said, because it makes it sound like validity is this really super important thing, which it really is. In the real world, when we're studying behavior, there's lots of ways we can do this. Case studies are methods of gathering scientific knowledge by studying a single individual. Now, think about how important the data would be if we just studied ourselves. Do we think about our own thinking as normal, in that a lot of people think the same way as us? Maybe, but that's not a case study. A case study, or a case method, as the book describes it, is a situation where we have a unique outcome that occurs. Now, let's go way back to Phineas Gage. Phineas Gage was one of the notable descriptions of traumatic brain damage. He was using a tamping iron to pat down the dynamite, TNT, that was being used to build the railway in America. Unfortunately, the tamping iron sparked on the rocks, and of course, sparks and dynamite, not a good thing. It blew up, and it launched the rod under his cheek and exited the top of his head, and it landed like 40 yards away. Now, the remarkable thing is, Phineas Gage lived. So he's remarkable because he suffered this traumatic brain injury, but he lived at a time where most people who suffered these kinds of accidents did not. And it was noted that physically he looked like Phineas Gage, but his personality changed. He didn't act like himself. At least that's what his friends said. So case studies can be invaluable in letting us study individual instances where, say, trauma occurs neurologically, and we can try to understand how does that person then perceive the world, knowing that they don't have these structures intact. We can then assume that the differences observed are likely due to the fact that brain damage occurred. While that is a really, really useful measure in studying instances of traumatic brain injury, it's difficult to plan and anticipate when these things occur. I also can't randomly sample necessarily because I don't know that there's more than one person who has the same brain damage, depending on what we're talking about. So we can't always randomly sample, which is just a technique for choosing participants in to be in the study that have an equal chance of being selected. So you can imagine if I was going to give you all a prize, some free grades, you'd probably want all of your names entered in a draw, like a hat, where I'd pull your name and you all had a chance to be selected because that's fair. And when we sample from a population, that might be the fair method to try to achieve, but it may not be practical. Because think about how do I find and make sure everybody has an equal chance of inclusion? You might think, well, let's use a phone book. I mean, fair enough, but are you listed in a phone book? Are your parents anymore? While it might be an okay method to find people, it doesn't make it ideal. I mean, we all have cell phones, but thankfully the numbers are not listed. Sometimes we have to use non-random sampling because we want to make sure that if we can get some people to participate, it would be great. And maybe we can't use a random technique. So if we want to find people just for the sake of convenience, we can execute a non-random sample just because it allows us, when samples in a population don't really matter, to get people to participate in the study. The advantage of random sampling, back up above, is that the sample should be a representative of the population from which they came. The reason this is really important is because we can generalize to that population then, meaning the results obtained really reflect the bigger population. So imagine that we develop a treatment for cancer and the sample who received the treatment, they all get better. We can assume then that of all the people with the same kind of cancer, that they would, on average, all benefit from the treatment. That's basically how we sample. We get some numbers. We think about the averages, the variability. We plot graphs. We compare groups that get the treatment, that don't get the treatment. And ultimately, we want to generalize to the population with some statistical, certainty. Our p-value would be less than 0.05, that the treatment works. Yay, we can treat your cancer. If the p-value, on the other hand, was greater than 0.05, we're really saying the treatment doesn't work, or that the people, unfortunately, we're trying to help aren't getting better. Hopefully, this makes sense. So, in an experiment, the researcher cannot observe an entire population. It would be impossible. So, we can draw samples. Remember, the population is the complete set of participants who might be measured of something, and the sample is a partial collection of people drawn from that population. It's the subset from which they come. I think that's hopefully clear by now. Is non-random sampling a fatal flaw of research? No, it's not, because sometimes they are representative of, you know, of a group, but we don't really care about the representativeness of something. And sometimes it's just a good starting point. And to do research, we can't be so strict that we consider everyone and everything needs to be there. Sometimes we just want to get people and grab their opinions on something as a starting point, not as an ending point. So learning about people does not necessarily tell us about all people, but it can still tell us a lot about something, whatever that thing might be. In the real world, do we execute replication? No, not really. We tend to extend research by tweaking the methodology a little bit, as well as the hypotheses. But should we replicate? I'll leave that as a rhetorical question for you to think about. We can also think of situations when we do research, like making the correct conclusion about something or making an error. So let's start with the easy. Imagine you go to the doctor because you think you're pregnant, and the doctor tells you, congratulations, you are pregnant. And the reality is, you are pregnant. That's a correct decision. On the other hand, if the doctor comes in and says, I'm sorry to tell you, you're not pregnant, and the reality is, you are not pregnant, well, that's also a correct decision. May not be the news you wanted. It might be the news you wanted, but it's still a correct decision nonetheless. Now, a type 1 error, I'll just read it out before we work with our example, occurs when researchers conclude that there is a causal relationship between two variables when there is not. This was the case with autism and vaccinations, saying the vaccines cause autism when they don't. But let's go back to pregnancy. The doctors come in the room and says, "Congratulations, you're pregnant." But the reality is you're not. We're not going to evaluate the qualifiers of what that might mean. Let's just say it's a matter of fact. A type 2 error, on the other hand, is when the researcher concludes there is not a causal relationship between the variables when in fact there is. In this example, the doctor comes in and says, "I'm sorry, you're not pregnant, but the reality is you are." Again, errors are not something that we can always know with a degree of certainty we've made. Remember, we're dealing with the likelihood of something happening by chance is less than 5%. That's the number that we just discussed a few slides ago. We never know reality. We have to use tests and measurements to try to come to a conclusion as reasonably as accurate as possible. And sometimes we make a mistake, and the mistakes can be significant. In the case of vaccines and autism, Andrew Wakefield lost his medical license for making up the data. So ultimately, the data used to draw the conclusion was fake. We strive to avoid the pitfalls of errors. Unfortunately, they happen. It's part of the cautious sort of optimism to science. We want to believe what the data tell us, which is why we try to find really good tests to detect changes of behavior, as an example, or in this case, pregnancy tests. You want to be certain and not make a mistake. Now, again, in the example used, you might think, well, you told someone they're pregnant when they're not. They're going to realize pretty soon with a type 1 error that they're not pregnant because they're not going to see the physiological changes that should be happening throughout pregnancy. Conversely, imagine telling someone they're not pregnant. What if they go out and celebrate and drink alcohol or do whatever you want to do, whatever you're thinking about if you wanted to celebrate not being pregnant? What if they're trying really hard to conceive and you just told them that they're not, but they are? I mean, the reality is in time, physiologically, things will change. And then it will become obvious that they are. So the type 2 error doesn't necessarily, or one error, persist forever in time, but it can lead to complications. Let's switch the example from pregnancy to cancer. Imagine your doctor says, "I'm sorry, you have cancer," when you don't. Imagine you start a treatment for cancer when you don't need it. How might you feel? What about if your doctor tells you you don't have cancer, but you do? We all know that this news would be terrible because the reality is the tumor would still be present. And over time, things would get worse to the point where by the time you detect it, it could be too late. So errors are something we're always striving to avoid because it would be costly if we missed them. So that's why we have really strict conclusions, meaning if we say you have cancer, we are 95% certain that you do. There's a 5% chance that we're wrong. Now, that's kind of the world we live in. But the tests that we have for things like cancer, it's even higher. I'm just using the numbers we have. I don't want to throw out other numbers that are used for various other assessments. We're just trying to keep the examples consistent with the 0.05 we talked about earlier, or 5% chance of making a type 1 error. That's really what that number represents, the likelihood that I've made the false positive. Psychology in class we talked about this. Is it a research crisis ongoing? Shouldn't we be replicating, and why don't we? And what do you think? It's replication experiments aren't really worthless, but they're not valued. Um, this is really a question for you to really think than it is for me to just stand here and just state whatever I think it is. So, is it a state of crisis? No, of course not. But why is replication important? Or is it? Should we be stuck on trying to spend all of our time replicating findings? And don't forget, there's a cost to doing research. Or should we be advancing knowledge by moving the goalpost just a little bit further along? What do you think? An important thing that we want to consider in psychology, and it's great that we're moving towards the end of this lecture and thinking critically about the evidence we presented with. Let's take the recent announcement that acetaminophen is somehow linked to autism. You might think to yourselves, is it? And when was autism first diagnosed? It's around 1911. And when did Tylenol get invented? That's around 1950. So the fact that there was observations of a behavioral change decades before the drug came to market, how can they be related? If we think critically about questions, it can help guide the way we think about the conclusions in really the best way possible. I'm not saying everything we consider would be unbiased. Of course, we have our own lens, how we see the world, but we want to make sure that we rely on the evidence and not just our opinions to tell us what we think might be true, knowing that it's almost impossible to know if something is quote unquote true. Why do people struggle to think critically? What do you think about this? A natural and intuitive way of thinking about evidence really worked better for hunter and gatherers than it does for large scale complex societies that we live in today. Now, the reality is sometimes it's hard because we like to hold on to our own opinions. We want to believe the world is the way that we think it is, rather than the way that it actually is. Your beliefs might shape what evidence you'll consider, which is something like a confirmation bias. You may Google and search things consistent with what you want to believe rather than what the general population tends to believe. You may look for evidence, you may avoid looking for evidence. You don't want to consider alternative opinions because we just don't. So scientists tend to be skeptical. We want to strive to make our observations as accurate as possible using reasoning and rigorous research to hopefully pinpoint what are the ultimate drivers for the behaviors we're interested in observing. Um, we're not Americans, so and I skipped over this in class too. So let's just ignore sort of the missing evidence, if you will, or challenges with research. But largely, it's that the most densely populated areas tend to be surveyed or participate in research, which could create a bias, especially with all the other um, rural areas of all the states that exist. But let's just ignore the American examples for now. It's also important when we think about research to consider doing what is right, morally, ethically, um, in whichever other ways you want to think of doing the right thing. We go to great lengths to protect the well being of you, our research participants, and we are bound by a code of ethics. We can only do so much to other people to learn about behavior before we could cause harm. And we are allowed to cause harm, but we are not allowed to cause harm such that it would be detrimental to you. As an example, I could test your pain threshold using like an ice bath or something. It doesn't mean about beating you or something to that effect. It's we can do it reasonably, but we have to have all these other protocols in place to make sure that in the event the worst case scenario happens, we have a way to make sure you're okay. How does this happen? We have research ethics boards, and it's really important that we go through them to conduct research with people. It's also critically important that we go through research ethics boards to conduct research with animals. Remember, animals can't advocate for themselves. I can't explain what I'm doing to them, so they can't consent, much like research with children. And the children can assent, they can say, yes, I want to do this, or no. But we have to have these mechanisms of uh, overviewing and conducting and overseeing our research to make sure we do the right thing, that we're truthful, we're honest, we share the credit for the work, the ideas, as well as the data. So we can't just make things up. It's important that we represent respect people. And this respect really comes to these codes of conducts. And in Canadian systems, you can look up the Tri-Council Research Ethics Policy too, and you can review it if you so wish on your own leisure. But when we do research, we ask for your informed consent to participate. We cannot coerce you to participating in the studies, meaning I'm not going to say, hey, do you want to do this study for $1,000? I can't promise you really high grades to come and do the research where you feel that you can't say yes. Historically, unfortunately, these were problems where people were mistreated, and that mistreatment to those people decades ago still lingers with people's lack of faith and support and belief that people who do research will do things honestly and do the right things. We have to protect you from harm. If I ask you how you like your job, and I want to know all the good, the bad, and the ugly of your job, I need to protect you. So if I go and provide a summary to your employer, I don't say, well, hey, well, Jane Doe hates this, and she really doesn't like it when you do that. That wouldn't be cool. I'd need to make sure that I remove things that could identify you and summarize things in a way that would protect who you are. It's not just the harm of, say, physical, it's the risk of something like losing your job. What's the risk benefit of me completing research and finding something that really, should I share this? Is it in the best interest of the group if I shared something that may or may not, well, be true? Deception can be used where I can mislead you about the true purpose of the study, but again, it has to be justified. And the most important thing we have to do if we're going to use deception is to debrief you about the study that occurred. You have to be told what the true purpose of the research is so that in the end, you know what it was. And also critically important is confidentiality. If you participate, we need to protect your identity and remove it from your responses so that we won't know it's you. And even if I did know it was you, I can't disclose it. I am promising you the confidentiality of a participant in the study. Therefore, I have to give that and honor that. In the case of animal research, trained researchers, psychologists, we have to supervise all of the procedures involving animals. And if we're going to cause harm or pain to an animal, it must be minimized, used only when alternative procedures are unavailable or could be justified. Anesthesia must be used when available if surgical procedures are used. Having conducted animal research, I can tell you that these facilities are amongst the strictest of facilities to conduct research in. You have to justify why you need animals for research in your application to do research with animals. If you're going to harm them, what's the rationale for why you need to harm them? What is the termination of life procedures that will be used? Because we can't release the animals to the wild when they're done. And you might think that that's cruel, but the reality is these animals have never seen the sun. They've been bred in a laboratory, shipped across provinces or the country to be participants in a study. And when they're done, the food they've ever consumed is given to them. The water is given to them. Their bedding changed. They can't forage. They would suffer a cruel death if you freed them into the world. Um, Plus some of the other things that we may need to do, just it's not practical to do it. And I can tell you from having done it, there's no pleasure in the termination of life of an animal. It's a necessity of the job of conducting animal research. And you have to make sure you follow every protocol to make sure that, again, it's justified and as harmless or as painless as possible. So the research ethics of animals and the procedures and protocols are extremely strict, almost more so than with people, just because we don't do the kinds of things to people that we can and do to animals. And maybe as a side note, it's worth noting that the poster in the adjacent lab when I did my master's said that the little white mouse has saved more lives than 911 ever will. All the cancer research, HIV, um, it's all been done with animals. It really is the ultimate sacrifice that they make for us to really learn about the things that can help humans and also can help us understand them. So comparative cognition is about animal um, research where we just want to learn about animal species as well. Not everything we use animals for is about us, but some of it is. We also have to respect the truth. Sometimes we come to conclusions that really we might be surprised with. And there's a large degree of, for lack of a better word, faith we have in each other to honor the data that we find, to not throw out data we don't like and find numbers that we do like. We want to report these results truthfully, what was done, what was found. And we do want to credit where credit is due. It should be ethically assigned. If a student came up with a brilliant idea, how would you feel if I stole your idea? Of course, you'd be frustrated. And we have to share that data when asked. So we can't just delete the data when we're done. We have to store it for an extended period of time, usually about 5 years. That is the end of really chapter two, which is a lot like our first real lecture of intro into psychology. And I recognize there's a lot there. You may want to go over things a few times. If you have questions, I would suggest to reach out. But hopefully, after reading the book and listening to the lecture, things start to make sense. There's a lot of gaps in terms of statistical knowledge that we're going to avoid because it's not for right now. But it's important that we think about the larger piece of what we're trying to do and how we do it, and why really doing your own research should start to sound really difficult because it is. Doing your own research requires the methodology, the ethics to do research, the methodology of what we're going to do, how to do it, when to do it, the data. What do you do with numbers? What's the conclusion? Did you make a mistake? Did you introduce a bias, a confounding variable? Research is complicated. It's why it takes years of practice to do it, to ultimately draw a conclusion which generalizes to the population. And hopefully, we don't make a mistake. And we try everything in our power through our training to avoid mistakes because sometimes they have consequences. And the examples I use, I apologize if they're a little bit forward, but they're real. They're real. And people have been misdiagnosed with cancer and they've had outcomes occur based on the misdiagnosis of something. And it's difficult. They're important, but they're really difficult lessons. So, with that in mind, we're going to move to the biology behavior next. We're going to jump into neurons. And I recognize that a lot of people take psychology for the mental health clinical aspect of what some of us do. But the biology of behavior is also important. And some of you may have interest in that. If you do, the next chapter is for you. Until then, take care, and we'll see each other soon.